Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel. Today's topic of discussion is basic electrical quantities. Our objective is to introduce the basic electrical quantities of voltage, current, resistance, and power. We'll discuss the units, common instrumentation used to measure these properties, and the means of calculating these quantities. Right up front, I want to clarify the title of this lecture, Basic Electrical Quantities. Realize we'll discuss the basic electrical quantities basically. I do not wish to get into unnecessary technical detail at this point. However, I do want to give you a worthy preview of common concepts that we will deal with over and over throughout the course of the Basic Electronics series. As such, I will make broad sweeping generalizations, wholly inaccurate simplifications, nebulous analogies, and use comical contrived examples. I want this lecture to serve as a quick peek inside Pandora's box before we smash the box open and a fire-breathing, bat-winged, thousand-tentacled monster explodes out of it. As we delve deeper into this lecture series, I plan to show you more and more of this monster, a tentacle at a time when it is appropriate to do so. I do not wish your brain to explode in sheer horror. Yet. The time will come when you are ready to face the horror full on, but first you must sharpen your wits, learn a couple basic block, check, strike combinations, and show up to class and lab every day prepared to train for battle. As much as I'm denigrating the contents of this lecture as basic and contrived, I'm embarrassed to admit I use this stuff all the time. Yes, I know all the details about the chemical reactions internal to a lead-acid battery. I know about Lewis definitions of acids and bases, and I know all about the subatomic detail of electron orbitals. But when it comes right down to it, I look at a battery and say, there's a box with two separate compartments. One side has a bunch of negatively charged electrons. The other side has a bunch of positive charges. The electrons want to get to that side and call it good. When you hook an electrical load like a motor or a light from one side of the battery to the other, the electrons have to travel through the load to get to the other side. Along the way, they impart energy to a load. It doesn't matter which model you use. The overcomplicated and time-consuming internal chemical reactions of the battery as a source of charge imbalance, or the quick and dirty mental image of a crowd of electrons plowing their way through an electrical load looking to hook up with a proton on the opposite side. The result is the same, moving electrons through a device. Which brings us to two basic electrical quantities I'd like to introduce, voltage and current. Voltage is why charges move. Voltage appears as a differential across something. Current is how many charges move in a given period of time. Current flows through something. The terms across and through don't mean the same things. Voltage and current are not the same thing, and they are not measured in the same way. Think about the terms across and through. Across means there are 2 points. Voltage is a measurement of the energy differential between 2 points. Through means there is 1 point. Current is a measurement of charge flow that passes through a single point. Across versus through, despite being non-technical terms, is the fundamental difference between voltage and current and speaks volumes about their nature and how to measure them. Let's use a simple model to illustrate across versus through and find similarities in our simple model between the basic electrical quantities of voltage, a differential across something, and current, a flow through something. Consider a box with two separate compartments. On the left side is a quantity of hot red water. Let's consider these characteristics positive. On the right side, there is an equal quantity of cold blue water. Let's consider these characteristics negative. There's a wall between them, and there's a difference in temperature and color across them. You can measure the difference using a 2-point measurement. It can be said that the left side is hotter and redder or more positive with reference to the right. Similarly, it can be said that the right side is colder and bluer or more negative with reference to the left. With reference to is an extremely important term to understand regarding voltage. With reference to means here is the point I'm comparing all other points to. With reference to your lab partner, you are smart and good looking. This is the person you want as your wingman when you're out on the town. You're going to get a lot more action when a potential mate is faced with the prospects of going home with you or going home with someone that smells like the reptile house at the zoo. With reference to also means it's relative in nature. With reference to your lab partner, you are a total catch. With reference to me, I mean, come on. You look like one of those demented boss-level characters from a bass fishing video game. Now let's talk about flow. With no passageway connecting the hot red side to the cold blue side, and given the wall between these two compartments is impermeable, no flow exists between the two sides. This being said, a difference still exists between the two sides. If one was to hook a pipe from one side of the container to the next with a water wheel inside the passage, seeking equilibrium, hot red molecules of water would move this direction, and cold blue molecules of water would move the other as both sides diffuse towards balance. As these molecules move or flow, they do work by spinning the water wheel, which is resisting flow. If the water wheel wasn't there, we'd have an uncontrolled mixture or uncontrolled flow. Given a controlled flow, we can measure the quantity of molecules that pass a single point in a given time period. This single point flow rate measurement is equivalent to current. Current is the flow or the movement of a physical particle, namely the electron. In this model, I'm showing an equal and opposite movement of both red and blue particles, so you'd think they cancel each other out. But realize in an electrical system, only one thing is moving, the electron. So there is a net movement of charges in one direction. That's the problem with these simplifications. They're only good to a certain point. As the water molecules continue to flow from one side to the other, realize what is making them flow is 1, the passageway between them, and 2, most importantly, the difference in temperature and color between the two sides. This difference is equivalent to voltage, and it is the reason why charges move or flow. Voltage causes current. Realize that the differential in our closed system, if there is no other outside source striving to continually maintain the imbalance, is becoming less and less different over time as red hot water moves one way and cold blue water moves the other. When all the water in our closed system is neither hot nor cold nor red nor blue, but rather a uniformly warm, uniformly purple color, we can say there is no difference between the two terminals of our energy source, nor will there be any flow exchange between them. We have effectively discharged our battery, and our load grinds to a halt. Moving beyond this simple model, understand that voltage is the reason why charges move. Voltage is the cause. There's an imbalance or difference between 2 points. This difference is measured using the units of volts, often abbreviated with a capital V, where a volt in actuality is a derived unit that equals 1 joule of energy per coulomb of charge. A coulomb is a means of packing up charges into a more usable number. Kind of like a dozen eggs actually means 12 eggs. Except a coulomb is a lot more than a dozen. It is a lot more. 1 coulomb equals 6.24 times 10 to the 18th charges. One can represent the concept of voltage in shorthand using a capital V. The movement of charges or current is the effect. The measurement of current must necessarily include a complete path for electrons to flow and must necessarily be a single point measurement somewhere in that path through which all moving electrons can be counted. Charge flow is measured in units of amps, often abbreviated with a capital A, where 1 amp in actuality is a derived unit that equals 1 coulomb of charges moving by a single point over a period of 1 second. You'll often see the concept of current represented in shorthand using a capital I, which stands for intensity. What limits, controls, or opposes current is our third basic electrical quantity, known as resistance. The unit of resistance is called the ohm, symbolized by this funny horseshoe-looking thing. An ohm is also a derived unit, where 1 ohm equals 1 volt over 1 amp. You'll often see the concept of resistance represented in shorthand using a capital R. On a very basic level, we can state that the effect induced in some system is equal to the cause over opposition. This should make sense. The more effort or cause given to a project or undertaking will undoubtedly yield more effects as long as opposition to your efforts remain low. If, however, opposition increases, the effects will be reduced. Given voltage is synonymous with cause, current synonymous with effect, and resistance synonymous with opposition, we can rewrite this relationship as current equals voltage over resistance. Looking closely at this relationship in either form, we can make the following statements. If opposition was held constant and cause increased, effects should also increase. Stated another way, same resistance, more voltage yields more current. Conversely, if opposition was held constant and cause decreased, effects should also decrease. Stated another way, same resistance, less voltage yields less current. Other observations are equally as valid. If cause was held constant and opposition increased, effects should decrease. Stated another way, same voltage, more resistance yields less current. Conversely, if cause was held constant and opposition decreased, effects should increase. Stated another way, same voltage, Less resistance yields more current. This extremely important cause, effect, and opposition relationship is known as Alms Law, which will be the most frequently used tool in your toolbox throughout the course of the entire basic, intermediate, advanced, and super advanced electronics series. I'll devote another entire lecture to DC Alms Law. In the meantime, just think in terms of cause, effect, and opposition. These terms and their relationship with one another should make sense on a very intuitive level. Let's now introduce the concept of power. As you're no doubt aware, power is energy over time and is measured using the units of watts, where 1 watt is equal to 1 joule of energy per second. Electrical power is also the product of voltage across something times the current through something. Power in units of watts equals voltage in units of volts times current in units of amps. Given 1 volt is a joule per coulomb and 1 amp is a coulomb per second, the units of coulombs cancel out, and we're left with the units of joules per second, or a unit of energy per unit of time, or a unit of power, where 1 joule per second is equivalent to a watt. Let's again use this simple model to illustrate power. Consider water under pressure hooked to a water wheel, where a blocked valve does not permit movement of the water. If pressure, equivalent to voltage, exists, but the water isn't flowing, equivalent to 0 current, the water wheel won't turn. High pressure times no flow yields no power. Consider another case where the water is flowing but exerting no force on the paddles of the water wheel. In this case, the water wheel still won't turn because the pressure or voltage is absent. High flow times no pressure yields no power. However, consider another application of this water wheel where both pressure and flow exist. The flowing water with a pressure differential exerts force on the paddle of the water wheel, and because it's moving, turns it. Power is consumed from our fluid and delivered to our output shaft. Parallels between this water wheel analogy and an electrical system exist. Power is only delivered to or consumed by a system when there is both a voltage differential across and a current through something. We'll discuss power calculations in later lectures. For now, I'm hoping this basic introduction should suffice.